this week's topic. This week's topic is actually measurements and data analysis. Normally, it's supposed to be taught by our tutor, Kevin, but I'll be the one handling it from now. So let's go straight into today's business. Okay, our lesson objectives are this. At the end of this lesson, you should be able to understand what SI units mean and also what derived units are. You should be able to also perform unit conversions with examples. And also, you should be able to apply the rules of significant figures in calculations. Also, you would also, by the end of this lesson, be able to differentiate between precision and accuracy. You'll also be able to identify and classify different types of errors, carry out data calculations, including standard deviation and error analysis. So let's go straight into today's lesson. What is measurement? Measurement can be defined as, or can be said to be, when you try comparing an unknown quantity with a known quantity. If, okay, let me break it down in this form. If you were to tell someone what 1 meter mean, you can't just with your mind just tell someone, okay, 1 meter is this length. You would have to have a reference which you would be referring to as the standard 1 meter. Then you tell someone this is standard 1 meter. Then this particular length that we are talking about is also 1 meter because it aligns equally with the standard reference being the normal 1 meter rule. So that's actually what measurements are. Measurements are trying to use the standard reference to compare another entity or quantity. So when we talk about measurements, we are talking about measurements, we are talking about comparing unknown quantities with known standards. So there are different ways we carry out measurements, and one of the major ways that they use in carrying out measurements is by using units. We know the measurements for length is with the units meter. The measurement for mass is with the unit kilogram. The measurement for time is with the unit second. The measurement for temperature is with the unit Kelvin. The measurement for current density is with the unit ampere. Amount of substance, as in chemistry, is always represented in moles, and so on. There are many measurements that are used, or there are many devices, units that are used for different measurements. So I believe we should be taking our notes down to write down this. So there are different types of units. We have CGS units and SI units. If some of us were present in the physics class, you'll be able to tell the difference between CGS units and SI units, because in that last class, we were taught what SI units are and what CGS units are. So for the sake of those that were not present, I'll be giving a quick explanation of what they are. Units generally are a form of measurements. They are a standard of measurements. So when we talk of units, there are different types of units. We have what they call the CGS units. The CGS unit is a kind of unit that is used to measure both length, mass, and time, and different other quantities. So while the SI unit is actually one of the types of units that is universal, it's not just within a country, it's not just within a selected country, it is universal. If you go to the US, go to UK, they use the same units for measurements. So that's why they call this SI unit. And SI units mean International System of Units. So in case you're writing down, you can write it down. SI units means International System of Units. I know it doesn't really look like what it's being called. It's called SI, but we are hearing international before standard. So that's just how they chose to name it, where I is international and S is standard. So moving on, we'll be going to our next slide. which is talking about derived units. So in physics, they call these derived units derived quantities. So they are actually similar. If you were learning physics, you would be taught fundamental quantities and derived quantities. I'm sure most of us here, we are familiar with those terms, fundamental quantities and derived quantities. So these are similar in chemistry. So for fundamental quantities in physics, fundamental quantities are quantities that are like the bedrock for other quantities to be created of. In our physics class, I remember using an example saying fundamental quantities are just like your alphabets. They are the starting point to create any word. They cannot be broken down any further. They are like the building blocks for other types of quantities. So while derived quantities are a combination of two or more fundamental quantities. So in this same light, it's when we talk about units, we are not talking, there are differences between units and quantities. So quantities are measured with units, but units are they are the measurements. They are what they use to measure quantities. So somehow, sometimes they interchange both of them. They tell you derived quantities, and they might also tell you derived units. So the difference, like an example of one of the different quantities and units, mass is a quantity, but its unit is kilogram. Mass is a quantity, but its unit is kilogram. So I believe you should be able to relate. The same way we have length being a quantity. Length is a quantity and its unit is meter or centimeter. So they are similar, and most times some people use it interchangeably. So let's move on. Derived units or derived quantities are, or let me use units since we are using units for this for our study. Derived units are units that are a combination of two or more units. Two or more units. Preferably, I would prefer saying two or more fundamental units. So when you combine two units, either the unit for mass, the unit for length, unit for time, unit for whatsoever, when you combine units of one, the unit of one quantity and the unit of another quantity, you will be forming a derived unit. A derived unit cannot exist alone. It cannot just be meter. When it's only meter, it's not a derived unit. It can be called a fundamental unit. But when it's a combination of two meters, that is meter times meter, like as you can see here in case of area, it is then called a derived unit. I believe I'm passing an information to you guys. So now, here I listed out some examples of these derived units. We have area being a product of two lengths, that is meter times meter, to give you area. Volume, meter times meter times meter, that is meter cube. And density, we have kilogram divided by meter times meter, or kilogram divided by volume, that's density. It's also a derived unit. And as I was initially trying to explain, we have different units. We have different types of unit measurements, if I would call it that. We have SI units and CGS units. I would like people to write this down, probably on your notes. Just probably draw a table where you write SI on one side, SI unit on one side, then CGS unit on the other side. I'll just give you some seconds for you to write it down. SI unit on one side, CGS unit on the other side. So I'll clarify what these two are, so we'll be able to pass the information I'm trying to give off. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, so I assume we've written SI and CGS on our notes. So for SI units, as I said initially, SI units, they are universally acceptable. They are accepted everywhere. That's on that SI unit, you write that they are universally acceptable. They are they are the units that are universally acceptable. While CGS units, it was an old standard unit. It was an old standard unit. SI unit is actually the modern one, while CGS unit was the old standard. It's in CGS units you'll be hearing stuff like inches when they're trying to measure length, or centimeter rather, when you're trying to measure length. Some other units will use foot, some other units will use inches, some other units will use different different units representing lengths at the same time. So SI units, as I told you to write, SI unit is accepted universally. while CGS unit was the previous universally accepted unit. So it is kind of outdated. CGS unit is outdated, and CGS means centimeter, grams, and second. Is a unit that is represented in centimeter, grams, and second. So under SI unit now, you would write mass is measured in kilogram, length is measured in meter, and time is measured in second. That's under SI units. Under SI units, you write mass is measured in kilogram, length is measured in meters, and second, and time is measured in seconds. Then under CGS unit, you'd write mass is measured in grams. Mass is measured in grams. Length is measured in centimeters. Length is measured in centimeters. And time is also measured in seconds. So these are actually, like, I'm trying to give you differences between SI units and CGS units. So as we can see here, we are basically focused on just SI units. We have area, we have volume, we have density, we have speed, we have force, we have pressure, and so on. So the SI unit for area is meters squared. The SI unit for area is meters squared. The SI unit for volume is meters cubed. While the SI unit for density, we know that density, the formula for density is mass divided by volume. So the unit is then kilogram divided by meter cube. So kilogram divided by meter cube. So for speed is the same thing as distance over time. So because distance is measured in meter, we have meter per second as unit for speed. As units for speed, we have meters per second. So also force is actually the unit for force. The SI unit is Newton. But this unit can also be, is just like a single name to give to the standard SI unit. Newton is also the same as kilogram meter per second squared. Kilogram meters per second squared. And the summary of, or the short form for mentioning this kilogram meter per second, instead of you saying kilogram meter per second is unit for force, you can say it's Newton. It's Newton. So I did not write this one I'm about to call out here to you, but I would like you to write it in your notes. It's called energy. Energy, the unit for energy. Energy is equal to, the same way we have it here, you just write energy equals kilogram meter squared. That's, instead of kilogram meter, you have kilogram meter squared over second squared. Kilogram meter squared over second squared. And the short name equals, the same way we have it here, equals, you write joules, 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 in brackets, you put it J. Joules, Joules, in brackets, we put J. So now for pressure, we have the formula for pressure is force over area. That's the same force we have here, force over area. So the unit now can be written as Newton per meter squared. I know some of us might be familiar with this thing, but I'm trying to break this down because of where we'll be heading to later in future. That's why I'm kind of going as low as this. So Newton per meter squared, and it's also written in short as Pascal, bracket open, PA. So I believe we all got that. So let's move on to the next slide. So this next slide, we're talking about unit conversion. Unit conversion. This is one topic or one portion of chemistry that is very necessary. You would get to understand it very well, because if you don't understand it perfectly, you would have issues when you are carrying out calculations in chemistry. So it's called unit conversion. It's actually one of the first topics in chemistry, but it's most time it seems like it's being overlooked, but it's very important, because once you understand this, most of your chemistry solvings would be less of a struggle. So let's go on to unit conversion. So unit conversion is actually talking, is not, I've not written that here, but I'm giving you like a brief introduction on what unit conversion is. Unit conversion is actually a phenomenon, if I would call it that, where you convert from one unit to another unit using a conversion value. I'm repeating myself. Unit conversion is a phenomenon or is a scenario where you are converting one unit to another unit. That is, you're converting either from SI to CGS, or you're converting from one level, maybe something like kilogram to gram, meter to kilometer, meter to decimeter, all those kind of stuff. So it's what they call unit conversion. And as I said initially, it's actually very crucial that you get to understand this very well, because if you do, most of your solvings, most of the common mistakes you make, where you see an answer, you see like 0.01 as the answer option A, you see 0.001 as the answer for option B, you see 0.0001. The answer is actually among those ones, but if you don't really know, you'll be wondering whether you made a mistake in your calculation. But the mistake is just actually because of negligence to unit conversion. So let's move on to an example. So the first example I have here said convert 3.6 kilometer to meter. 3.6 kilometer to meter. So if I would have said, assuming our mics were open right now, I've asked how many of us knew how many kilometers make 1 meter? Or let me open the mic and here, I'll be asking 3 conversion units, and I would like to, if you know the answer, I would like you to just identify by raising your hand. Then I'll open your mic. The first question is, okay, it's a three-way question though. It's a question I'm asking you. How many kilograms? You could write on your note, how many kilograms make 1 gram? How many decimeter make 1 meter? And how many millimeter make 1 meter? It's a 3 question in one. If you know the answer, I would like you to raise your hand. Raise your hand and I would open your mic. The question is, how many kilogram make 1 gram? How many decimeter make 1 meter? And how many millimeter make 1 meter? Can you guys hear me? If you can hear me, please, I would like you to just give a reaction. Let me know. If you can hear me, please, I would like to see okay, I can see success. I can see Christian. Okay, thank you. I can see faithful. So let me see the question I asked the actually basic questions, but there's actually one I'm observing for. Or let me just go straight to that one. How many decimeter make 1 meter? That's the main question I'm trying to ask. How many decimeter make 1 meter? If you know the answer, just signify with your hand. Okay, I'm seeing Jesse. Okay. Jesse, you can turn on your mic. You can turn on your mic. Jesse, turn on your mic. You let me allow Christian. So Christian, you can speak up. Christian. Okay, maybe speak up. Just speak up, or you could drop your answer in the chat, session, because I don't know if you're having an issue. Okay, I can hear you now. Sorry, I think it seems like my volume was low. So speak up. If any of you that has the answer, maybe Jesse, go first.
I don't know where to turn on my mic.
Okay, no, I can hear you now. I can hear you now. Just tell me the answer if you know the answer. How many decimeter make 1 meter?
How many decimeter make 1 meter?
Yes. Yeah, yeah,
100.
yeah. How many decimeter? Okay, I can see some persons on the comment section. They're saying 10 decimeter make 1 meter. Okay, thank
I
you,
said
Jesse.
100.
Yeah, yeah, thank you, thank you. So the correct answer is actually 10 decimeter makes 1 meter. So 10 decimeter actually makes 1 meter. So in case I ask another question, you should just your mics has been permitted to turn on. So just click your mic icon, even if it's still showing something like as if it's not disabled yet. You are free to just turn it on and speak. So your mic has been allowed now, so you can speak when you want to speak. Okay. So let's go on to where we are at. So for units of conversion, I would like you guys to write on your notes. I'd like you guys to write on your notes. For decimeter, we have 10 decimeter is equal to 1 meter. 10 decimeter, 10 decimeter is equal to 1 meter. Also, we have that 100 centimeter is equal to 1 meter. The same way we have 1000 millimeter equals 1 meter. So these are, let's say, the common conversions you will see within chemistry. You usually see either moving from meter to centimeter cube or to dm cube or just something within meter and decimeter, or meters and centimeter, meter and millimeter. So it's important that I would draw this line. So in the same way as we have for 10 decimeter making 1 meter, we have the same thing being applied for liter. So the hack behind this thing is when you see the word, when you see the word decimeter, when you see dm, just know that it is 10 of the d that would make the thing in front. So if you have something like, let me say we had deciliter, let me say you have something like deciliter, or yeah, deciliter, dl, and they said how many deciliter make 1 liter? How many deciliter make 1 liter? The hack is when you hear the word deci, it's always the same. It's going to be 10 deciliter will also make 1 liter. So also when you have centiliters like cl, how many cl are in 1 liter? It's also 100. Cents represents 100. So that's the hack. When you hear the word cents, it means 100. When you hear the word deci, it usually means 10. Deci, decagon, the same vein. Deciliter is 10. Then when you have milli, if they give you ml, and they said how many makes 1 liter, it's the same way. You have 1000 milliliter is also equal to 1 liter. So I'm calling out this thing and I'm writing these things out because I will need you guys to write it, because we'll be going into somewhere where you'll be doing extra conversion, where you would not just be moving from decimeter to meter or centimeter to meter. You're moving from centimeter square to meter square, stuff like that. So I would like you guys to write this down. I would like you to write this down, all this I wrote here in your notes, such that when we start doing this advanced level of conversion, it will be easy, it will not be complex. So for kilometer, when we have I would say it like this: moving downwards, we move downwards from meter. When you move from meter, moving downward, you moving meter to decimeter to centimeter to millimeter to micrometer to picometer. That's how you move when you move downward. But when you move upwards, you move meter to decameter. Decameter, not decimeter now. Decameter. Let me do that now here. So decameter is bigger than a meter. So 1 meter now, in that case, is now meter. You say 10, sorry. For that, for the case of decameter, you would have 10 meter is equal to 1 decameter. There's another one that is higher than decameter, which is hectometer, which is 100 meter is equal to 1 hectometer, HM. Let me put the spelling here, hecto, then meter. So this is decameter. Then all this other one, this is decimeter, DECI. So we will not mistake it. So if you look at this now, okay, let me first complete this query. So at this point here, when we got to, where is this? Okay, when we got to decimeter, let me give this another color. These ones, they are the smaller forms. 1 meter is bigger than all these ones, decimeter, centimeter, millimeter, and downwards. 1 meter is bigger than them. So, but when you start moving upwards, that's when you get above hectometer, we have kilometer. So for that one, we have 1,000 meter is equal to 1 kilometer. So I know this is sounding like it's looking more like primary school stuff, but actually these are like the basics, where if you actually made a mistake or if you didn't really get it, then it might become confusing to you. So these ones are the positive ones, they are higher, they are the bigger ones, they are bigger than meter, while these ones are, I don't know if this color is okay. Let me just make it something that will be able to cause a difference. Okay, yeah. So these ones now, they are bigger than meter. They are bigger than a meter. So if I wanted to have put a boundary or like a base, I would say 1 meter is equal to 1 meter. Is equal to 1 meter. So this is like the starting point. So above 1 meter, these are the larger ones. Below 1 meter, these are the lower ones. I don't know whether we get this. So this is how we convert. So even if you don't see meter, you see liter in replacement. That is LITER. Or you see gram, or you see any other quantity, and you use that, but you see the prefix was hecto, kilo, deca, deci, centi. These same laws apply to it. These same laws that govern all this, they apply to it. So now I would like you guys to write this down or possibly take a screenshot of this so that you'll be able to make reference to it when I move forward. So now the example we have here, we said the conversion was convert 3.6 kilometer to meter. So now this is where it actually gets complex. Now there is actually, I think what I prefer to call my own rule in trying to do conversion. So that rule is this: when I have conversion, I would first need to know whether I'm converting from a smaller unit to a bigger unit. So from kilometer to meter, it's from a bigger unit, because if you look at it now, this one's upwards. Kilometer is among the big guys, is the blue guys. So it's among the big guys. So when you're moving from kilometer to meter, you are moving from a big quantity, from a big unit to a smaller unit. And when you're moving from a big unit to a smaller unit, you would multiply it by the value behind the smaller unit. Moving from kilometer to meter, you multiply whatsoever you're having by, you multiply what you have here by the smaller unit. So such that you have 3.6, you're moving from 3.6 kilometer to meter. the units behind meter is 1000. So that's what you use to multiply the value of the kilometer. I don't know whether I'm making any sense. So the idea is you check if you're moving from a bigger unit to a smaller unit. When you're moving from a bigger unit to a smaller unit, you multiply by the factor. That's the 1000. But when you're moving from meter to kilometer, that's from a smaller unit to a bigger unit, as mean moving from meter to kilometer, moving upwards, you would divide. So assuming this question was the reverse, assuming this question was reversed, assuming this was meter and you're converting to kilometer. Instead of times, instead of multiplication that we have here, it will be division we'll be having here. So it will be divided by 1000. That's what we have done. So let me take this back to what we had in the question. So the rule I'm giving you guys here is when you are moving from a bigger unit, when you are doing any conversion, the first thing you should check is, are you moving? This should be at the back of your mind. These things here, especially these 6 levels, or if I call it 7 levels, they should be at the back of your mind. So when you check, are you moving from big level to a small level? If you're moving from big to a small level, you will multiply it by the value, either 1000 or 100 or 10 or whatsoever. But if you're moving from a smaller value or a smaller unit to a bigger unit, you will divide by that value, by the 1000, 100 or 10, you divide. I believe this should be as clear as possible. So now let's see example 2. Example 2 says convert 120 centimeter to meter. So first thing, as I said, you will check where are you converting from. Is this smaller than this? Which of them is bigger unit? So looking at this chart now, we have centimeter, comparing it to meter. This is the base, meter. So you compare, is it beneath meter, or is above meter? It's beneath meter, so meaning it is smaller. You're moving from smaller units to a bigger unit. And when I say when you're moving from a smaller unit to a bigger unit, you would divide by the value of that smaller unit. So 100 centimeter to meter, you'll be dividing the centimeter you have by the value here. So you'll be dividing 120 by 100, and that will be giving you 1.2 meters. So this is just like a simple hack, kind of, if I will call it that. When you're moving from a lower unit to a bigger unit, you divide. When you're moving from a bigger unit to a smaller unit, you multiply. And what are you multiplying with? You're multiplying with these factors that are behind each of these here, these factors here, 10, 100, 1000, 10, 100, 1000. So that's just, that's the hack. So this should be at the back of your mind almost every time, because most conversion will always be within this same frame. Especially conversions that are involving meter, liter, grams, will usually be within this same frame. So now we'll be showing where we have more than just, when you're not just converting from just kilometer to meter, when you have something like kilometer per hour and so on. But let's move on to our next slide first. So for our next slide, we have significant figures. So this is actually I call it junior secondary school topic. Significant figure is common. We'll say convert from one significant figure to two significant figure, or convert from just like that. So what significant figures are? They are they are real numbers where you have actual numbers that are not zero. Especially when the trick behind, sometimes there are some questions that I will see someone will tell you convert from one decimal place to another decimal, to maybe from 2 decimal place to 3 decimal place. They will tell you round off. They will tell you convert from significant figure to another significant figure. And the confusing portion is when you have stuff like this. This number 2 case. When you have stuff like this, number 2 case is the most confusing part when you are doing significant figures. So when you are doing significant figures, there are three types that the form questions can be. The second one is actually the most tricky, where you have leading zeros, or where you have zeros before the first number that is not zero. So for the first case now, we have where all non-zero digits are significant. So, okay, no, this first one is trying to talk about all non-zero digits are significant. This is just like definition. Every digit that is not zero is significant. However, this rule would fail when the zero is between two numbers or is between another number. So now that's what this rule 2 is saying. Converting significant figure. If you had some, let me give an example. When you have something like this, you have something like 3 4056. And they say convert it to 3 significant figure. This is the first significant figure. You always start from this end. You start from here 1, 3. That's the first one is 1. The next one is 2. Then the next one is 3. So this is the third one. And the reason why you are including 0 is because before 0, you have been seeing real life numbers, that is normal numbers that are not 0. So because of that, 0 will be counted as a real number, because these guys, I'll say these guys, they are protected 0, that you cannot know that 0 is not really a real number. So it's not necessarily a real number per se, but it's not really a non-zero number. So this one is a normal number, we know. Okay, this one is a normal non-zero number. This is another non-zero number. This is another non-zero number. So if the question was to find or convert this to 3 significant figures, converting this to 3 significant figures, our answer would be, sorry, our answer would be okay, sorry for that. I hope you guys can still hear me and see me. Hope you can still hear me and see me. If you can see me, put your hand up if you can see me, or you just give me an emoji if you can still hear me and see me. Can you guys hear me? Okay, thank you. So let's move on. 3 significant figure, they ask us to convert this number to 3 significant figure. So you'd always start from this end. You count 1, 2, 3. So you check the next number after it. If it is up to 5, the normal rule, you know, if it's up to 5, it will turn to 1 and add to the last number here. So since this is up to 5, it will turn to 1, and it's turned to 1 and be added to this place, and everything will turn to 0. So your answer will be 34100. So I believe this is common, or we understand what this one means. This is how to convert from 3 significant figure for normal, where you have real numbers or normal numbers starting from the beginning. So it becomes tricky when you now have stuff like this, where you have 0.00 something, and they are trying to ask you to convert it to maybe same 3 significant figure. Let me give you an example: 0.01334 or 335. And they say convert it to 3 significant figure. Someone will think, okay, since we are starting from the end, we will count 1, 2, 3, and this will be the 3 significant figures. But because of these first numbers before, they are not non-zero numbers. The significant figure will start from when we get to the first non-zero number. So this is going to be your first significant figure, your second significant figure, and your third significant figure. So you would then convert this 5, you round it up to 1 and add it to this. So your answer, and this was converted to 3 significant figure, your answer would be 0.0124. So this would be your answer in this case. So this is one of the cases that actually brings confusion most of the time, when you have non-zero numbers starting a number that are trying to round up to 3 significant figures. So when you have non-zero numbers, when you have zeros starting before it, you would look for where the first non-zero number starts from. Then you start counting from that number. So the third case is common. So when you have trailing zeros, the same thing that happened here. The non-zero number will shield other zeros, making them treat them like real non-zero numbers. So if you have something like maybe 4.0 or even 4.00145, and they say you should convert this to 4 significant figures, you will count, this will be your 1, this will be your 2, 3, 4, and this will be your 4 significant figures. Then you check the next number to round it up or round it down. So that's actually the rule for 3 significant figures. I'm sure some persons might be having that confused before, but I believe with this explanation it should be clear. The only place where you would observe a different rule is when you have zeros starting. Once you have zeros starting, you change the rule. So let me see whether we can hurry up for the sake of time. to something else. So this is the examples for what I just gave now. So they said to 3 significant figure. So I would like, let me see. I would like you guys to just hurry up and give me the answers to this on the comment section. Let me just give you a minute. You guys should give me the answers to these questions here. So this one, convert these to, I'll change this one to 2 significant figure. Then this, to convert this to 3 significant figure. Then convert this to, let me put this as 5. Then convert this to 3 significant figures. So I would like to see your answers as soon as possible in our comment section. Just write the answers. You don't need to put the question. Just tell me what the answers for this is. The first one is this one to 2 significant figure, this one to 3 significant figure, this one to 3 significant figure. So just hurry up, drop your answers in the comments section in our chats. Let me see. So drop your answers. I'm waiting for you guys. We have 1 minute, so I would like you guys to just hurry up and give your answers. Christian, I would like you to put your hands down. You are still raising up your hand. I don't think, or are you? Do you have a question? One Umaru Christian, you're raising your hand up. Are you raising your hand up deliberately? Okay, let me bring it down. So I'm waiting for you guys for your question. I'm waiting for your answers in the comment section. I'll just give 15 more seconds. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. So we'll be leaving, and whoever gets the correct answer in the comment section. I was supposed to give a bonus, but nobody gave me the answer. So let's solve it ourselves here. So we have the first question, we have 0.00456, and we are asked to convert it to 2 significant figures. So the first significant figure is not this, neither is it this, because the rule says when you have 0 starting, 0 is not a significant figure when 0 starts. But when it is in between 2 non-zero numbers, it is among a significant figure. So this is where the significant figure started from. So this is your first significant figure, the second significant figure. So if you're rounding this up, your answer will then be, your final answer will then be 0.00, sorry, 0.046. That would have been your final answer. So that would have been your final answer. So the correct answer is 0.0046. So for this one, the significant figure here, the first significant figure is 1, the next is 2, and the third is this, is 0. So to round this off, our final answer would be, this is, since this last 0 is not up to 5, it will just be remain as it is. So our final answer would then be 1, 2, 0, 0. So it did not change. That will be our final answer. In case you have, in case you don't understand how, or you have a question, I would like to see your hand up. So this third one now, it's to 3 significant figure. We have 1, 2, 3. This is the third significant figure. So rounding this up now, 5 is up to 1, 5 is up to 5. So we round this up, you'll be having your final answer to be 3.41. So that's going to be your answer. So this is your answer for this significant figure? Let me see if anybody's hand is raised up. Oh, marvelous! You gave your answer late. If not, I would have given the person that got the correct answer. I'd have given the person 2 gig, but nobody gave me the answer correctly, so my 2 gig is remaining with me. So let's go on. Let's go on. So calculation example. So this one is almost the same thing. It's just you do the calculations first. 2.3 times 4.56, whatsoever is your correct answer, you then convert it to the significant figure that you're looking for. So this question, they are probably asking you to convert it to 2 significant figures. So when you check this question, they're asking you to look for it in 2 significant figures. So when you multiply this, you'll be getting, when you multiply 2.3 by 4.56, you'll be getting 10.488. So to 2 significant figures, it will be 1, 2. This is your first and second significant figure. So this is not up to. This is not up to 4, is not up to 5. So because of that, you round this down. So this will become 0 and every other thing will remain as 0. So the answer is supposed to be 10. The answer is 10.000, but 0 after decimal point is as insignificant as we know. So the answer is 10 as 10. It's 10 as 10. So that's for sorry. So that's for this example. So let's hurry on to the next slide. So for this now, we're talking about precision and accuracy. Precision and accuracy. So precision is actually how close repeated measurements are to each other. Precision is talking about how close repeated measurements are to each other. So when we have something like maybe 1.45, we have 1.43. Okay, let me put it down. Let me put it here. We have 1.456. We have 1.455. We have 1.45 or 461. We have 1.4454. So with this now, this number, this first two and this last one, they are precise number because they are close to each other. This and this, they are precise. So if they were to ask you which of these numbers are the precise number, these ones that are closest to themselves, 5, 6, 5, 5, 5, 4, they are close. So these numbers, they are close to one another. So they have high precision. They have high precision. So they don't need to be the correct answer, so long as they are close to themselves. Even if the correct answer was supposed to be, maybe you solved or you carried out an experiment, maybe you carried out a titration experiment, your first answer, your first theta value was this, second theta value was this, and your third theta value was this, then your fourth was this. Even if the real value, the real answer is this, 1.461. When they ask you which ones are precise, when you're talking about precise or precision, you talk about which ones are close to each other. They don't necessarily need to be correct. They just need to be close to themselves. So these are the numbers that give high level of precision. So precision does not mean the answer is accurate. So precision and accuracy, questions on this usually come out that when a number is precise, does it mean it is accurate? So a number can be precise, or a group of numbers, they can be precise, but they are not necessarily accurate. For numbers to be accurate, they need to be close to the actual value, or they need to be the actual value itself. When you talk about accuracy, you're talking about how close something is to the actual value. So it's just like as though, I don't know how many of you have seen this Korean movie that they call Jumong, where they were this guy, there was one time it was a test where they were shooting a bull's eye arrow with arrow test. The fact that someone shot maybe 3 arrows and the 3 arrows hit their point, they hit the same point, but maybe he did not hit. Let me see whether I could explain some. Let me see whether I can illustrate it with probably a shape or so. Okay, for the sake of this in operation, I would have to just remain the way I am. So you happen, let's assume I was trying to target this box, and let me use this our box here. This our display box. Maybe your target was to shoot the arrow to hit this measurement spot. This spot where they put measurement. The target was to hit it. Then you shot your first arrow and it got to this point. You shot your second arrow got maybe to the next one here. Then your third arrow also got to this point here. Your shots were actually precise, but they are not accurate because the real target was this. This was the real target here. So your shots were precise, but they were not accurate because for them to be accurate, they need to be close to the real target. So I believe this should be a clearer explanation of what the difference between precision and accuracy is. So something can be precise, but not accurate. So for you to say that something is accurate, it needs to be actually close to the real value or the actual value. For you to mention accuracy, you need to know the actual value. So like this here, we see this is an example here where they gave us 3 measurements. They gave us 3 measurements and they said this is the actual value, the targeted value is 10. Then we had what they call it, we had 9.8, 9.9, 10.1. So in relationship to 10, these values are accurate, and at the same time they are precise because they are close to one another. So you say that these measurements are accurate and precise. However, this one's here, we have 12.1, we have 12.0, we have 12.2. Sorry, we have 12.2. So comparing to their precision, they are actually precise, but they are not accurate. The reason why they're not accurate is because the real target is to be getting 10. So because you are far, your answer is far from this, though they are close, they are precise, they are not accurate. So I believe this should be able to explain or clarify us on what precision and accuracy is, because questions on this usually come out sometimes. I've seen it in some past questions. So let's move on to the next slide. We have errors. Let me see how many more we have because our time is just running like as though. So we have errors and standard deviation, and let's see how fast we can go. So for errors now, we have different types of error. We have systematic error, we have random error, we have human error. These are basically the major types of error that people mostly talk about. These are the major types of error. These are the major types of error. So the first one is systematic error. The first one we have here is systematic error. So systematic error, they are errors that happen, they are repeated and consistent error. So they are usually caused by faulty instruments. They are usually caused by faulty instruments. While random error, they are unpredictable errors. Like it's not necessarily your fault. They are caused by either the environment. So this kind of random errors are kind of errors that would happen maybe if you're trying to observe maybe a white paper and the room is dark. You might not see the paper as white. You might say the paper is not white. It is maybe off-white. So it's not really your fault. It's an error that happens as a result of something that is happening around the environment. So this kind of error is grouped as random error. So while human errors are mistakes in readings or handling the instrument. So let's assume now you were trying, like this kind of human error is maybe if you are trying to mix two things. Let's assume you want to create a neutral solution. You're supposed to be mixing maybe hydrochloric acid and sodium hydroxide. You're supposed to mix both of them. Then instead of you to take hydrochloric acid and sodium hydroxide, maybe you took hydrochloric acid and another acid, and you don't know that both of them are the same. You started mixing them, and you're reading, you start getting one awkward reading, or maybe you're even supposed to use sodium hydroxide and you're using sodium triiosocarbonate as your base. You're not getting a reading that is completely different from what it's supposed to be. So this kind of error is not the instrument that is the fault. It is not the environment that is the fault. It's actually you, the human, that is the fault. So these are the 3 types of error that you have. Errors that are caused by the instrument, errors that are caused by the environment, and errors that are caused by the human that is carrying out the experiment. So these are errors that are grouped as systematic errors, random errors, and human error. So Ways to minimize this error: use better instruments, carry out experiments repeatedly, and also ensure that you, that is the human that is carrying out the experiment, you get proper training as a human. So this proper training would fit off or would accommodate for human errors. Repeated measurements will accommodate for random errors, because if wind is blowing, maybe we're trying to read something, or maybe somehow the wind that was blowing at the beginning might not be the same at the next time you're taking the same experiment. So when you carry out repeated experiments, it can help to cover up for random errors. So the use of better instruments, check your instrument very well. These are ways you can minimize these kinds of errors. So let's go on to the next slide for the sake of time. So we have standard deviation. So this standard deviation is the same standard deviation that we know in maths. And I will not really be dwelling much here because it's something that we should know in maths already. The formula for standard deviation is square root of the summation of any number minus the mean of that number, all squared, over total number present. So the standard deviation formula for standard deviation is just square root of the summation of x minus x bar, bracket close, raised power 2 all over n. So to calculate the standard deviation, you'd always need to get the mean. Then once you've gotten the mean, you check the individual values that you're given, subtract them from the mean, each of them subtract them from the mean, take their squares, then divide it by total number of digits that you have. So in this case now, we have the values we have is 5, 7, and 9. So the mean of these numbers, adding all of them, then dividing them by the total number, we have 5, 7, and 9. That is 3 values. So you add them up and divide them by 3. You get 7 as your mean. So having gotten your mean, to get the standard deviation, you take 5, subtract it from the mean. That is 5 minus 7. And what you get, you take the square of it. Do the same thing for the next one, 7. 7 minus 7. Whatever you get, you square it. Do the next thing for 9. 9 minus 7. Whatever you get, you square it. Then once you've gotten all these answers, you add them all together. Then divide them by 3, or by the total number. There are 3 values divided by the 3 values. Once you've gotten that answer, you then take the square root. This is what we had here, 8 over 3. Then you take the square root of 8 over 3. You have your standard deviation, which is 1.63. So I'm hurrying up so we could see whether we could take questions from any of the places where we've been studying so far. So here we have errors. Now we have some other type of mathematical errors now, where these ones are not just the definitions of those types of errors. These ones are the calculations for error. We have absolute error. We can calculate the absolute error by knowing the true value and subtracting it from the measured value. Once you've gotten it, you then take the absolute of that value. You'll be able to get the absolute error. Absolute, that is, you remove it. It's a negative value, you remove a minus sign. With a positive value, you still leave it as a positive sign. So that's what absolute error, how you take absolute error. As when you had maybe the measured value to be 5 and the true value to be 7, you will do 5 minus 7. 5 minus 7 will giving us minus 2. So the absolute of that will be giving us 2, because you will remove every minus sign after you have taken the difference. So the absolute error will then be 2. So for relative error, you would have gotten your absolute error first, then you divide it by the true value. So these are just straightforward. Percentage error, once you've got percentage error, once you've gotten the relative error, yeah, you just multiply by 100. So that's how you do these calculations of error. So I think I've seen questions under this topic: absolute error, relative error, and percentage error. So this is an example showing it. We have a measured value of 47. Then we have the true value of 50. So to take the absolute error, we'll subtract the measured value from the true value. So that's 47 minus 50. And that will be giving us 3. Normally, it's supposed to give us minus 3, but because of this absolute sign, the minus will go off. So we'll be having 3 as our absolute error value. So then to get the relative error, you divide the absolute error by the true value. As you can see here, the true value is 50. So dividing 3 over 50, we're having a relative error to be 0.03. Then to get the percentage error, you just multiply the relative error by 100. So that will be 0.06 times 100, and that will be giving us 6%. So I think That should be all for this session. So let me just take a quick recap. We talked about SI unit, and I told you that there are different types of units. We have SI units, we have CGS units, and I gave differences between SI units and CGS units. I gave differences between both of them, where I said that SI units are universally accepted, while CGS are outdated. SI units for kilogram, we have for mass, we have kilogram, for length, we have meter, for time, we have second, and CGS, I gave you the value there. And I gave you, I said derived units is when you have combination of two units, maybe length and kilogram, length and mass, you combine two. That's how you get derived units. We talked about unit conversion, and under unit conversion, we talked about converting from higher valued unit to lower valued unit, and from lower valued unit to higher valued unit. That's when we had centimeter to meter, or from decameter to, and so on. So though this class was supposed to be, that portion I was supposed to go into deeper teachings under that, but probably I would make, or we might make up time for it in another teaching. Then we went into rules for significant figure, where we clarified zero and non-zero figures, and how we find significant figures for that. I explained precision and accuracy, differentiating which one is what precision means and what accuracy means. I talked about errors and the types of error and how to minimize errors. Then we dealt with standard deviation and error analysis. So this is all for your week 1 night class. So if you have questions, I will be taking in questions now. So if you have questions, okay, see, sir, please, I did not get precision and accuracy. Okay. I'm seeing a question on the chat room where someone, Boma, I think Boma should still be on the call. Yeah, he should still be on the call. Boma Jax. He asked a question. Boma, can you hear me? If you can hear me, I would like you to wave. Boma, if you can hear me, I would like you to wave your hand. Boma Jax, I would like you to wave your hand if you can hear me, so I would answer your question. Okay, even if I wish he could hear me, so I'll probably answer his question now. Boma Jax. Boma Jax, I don't know if you can hear me, but I just hope you can hear me. If you can't hear me, okay, thank God you can hear me. So you were asking that you did not really get what precision and accuracy meant. So now let me use this our screen here. I believe you can still see my screen. You guys can still see my screen. So assuming I was to be an archer, and my target here, let's assume this is our screen here, we have this here, and my target was to shoot this center man, shoot an arrow on this center man, and I had like 3 arrows to shoot, or 3 arrows to aim with. If I shot my first arrow and my first arrow touched, probably touched gracious, my second arrow also touched gracious, my third arrow also touched gracious, someone would think, wow, this guy is a good guy. He's precise. His shots are accurate. The fact that he hit 3 shots at the same point does not mean he's accurate. It just means he's precise. His targeting was precise. So when you talk about precision, precision does not have to be. Precision is when you have different values that are close to themselves. Different values, they are close to themselves, but they are not actually the correct answer. So as means someone wanted to guess your age. Let me say, Boma Jack, someone see you ask a question, say, who in this room can guess my age? Then people said, maybe your age, let's assume your real age is maybe 21. Then people started saying you are 17 years. People say you are 16. People say you are 18 years. Most of these people, they are having similar guesses. Their guesses are seeming precise because everybody is within the range of 16, 17, 18, 16, 17, 18. They are having precise guesses, but they are not actually accurate because your real age is 21. So now when you say something is accurate, the thing has to be close to the real value. So anybody that is guessing 21, or anybody that is guessing that their guess was 20, they are guessing your age was 20, they're guessing your age was 22, they are precise because they are close to your real age. And they are also accurate because they are accurate because they are close to your real age, and they are precise because they are close to one another. So as mean 3 people guessed 21, 20, 22, maybe another person gets 21, another person gets 20, 22, but they are close. So long as the values are close to themselves, they are said to be precise. But when the values are far from themselves. They are not precise. However, when something is precise, it does not mean it is actually accurate. So it's only accurate when it's close to the real value you are targeting. So I believe I should have cleared you out on that. So let me move to the next question. If I explain it clearly to you, I would just like you to just give a thumbs up, so I would know that you are clear on what I just explained. So now someone was asking, okay, thank you. Are you asking a question or you are waving your hand? Okay, let me assume you. If you have a question, you could open your mic, unmute yourself and ask a question if you have a question. Boma, if you have a question, you can unmute yourself and ask. Okay, you are not asking a question. So, okay, Jessie, she asked a question on the comment section. She said, why is 47 minus 53? So, okay, Jessie, the answer was not actually 3. What made us put the answer as 3 was because of this. If you look at this our slide. Let me go back to the slide. So if you look at it, this is it here. This dash that we see here, this dash here, and another one here. These two things we see here and here, they are called absolute signs. So even when you do 47 minus 50, the real answer is minus 3. But because of the presence of this absolute sign, every minus you get within this absolute sign will be removed when you are getting your final answer. So if you get it as you got minus 3, your answer it's supposed to be here. Maybe you would have written equal to, maybe, let me see. Maybe it's supposed to be absolute minus 3 absolute, then equal to. So I think this is how it should be. So you would actually get minus 3. Then to remove this absolute sign, you then, every minus sign in between this would remove, and you have your final absolute answer to be 3. So I believe I have answered your question, Jesse. So the next question said, sir, about the significant figure 12000, sorry, 1200, can it be written as 1.2 times 10 to the power of times 10 to the power of 3? Probably when given in a question, yes, it is the same as that. It's the same as that, but this is actually represented in standard form. 1.2 times 10 to the power of 3 is in standard form. So if they're asking you for significant figure, preferably don't write it as this. Just write it as this if you are asked for significant figure. However, if you are solving and you just got your answer, you can leave your answer as this. You get? So you don't necessarily, if they did not ask you to put it in significant figure, you can put it in standard form. But if they specifically ask you to keep it in standard form, in significant figure, it will be best you don't put it in standard form in case whoever is marking it is not already conversant with conversion to standard form. So that's the answer to your question. So I would like to take one more question or two more before we round up. If you have another question, I would like you to raise your hand. Thank you. Omojola Marvelous. Omojola Marvelous. Thank you. So let me see who has another question. If you have another question, I would like to see your hand. I would like to see your hand. If you have another question. Okay, let me see. I'm assuming that there is no other question. So for the sake of time, we are 29 minutes to 10, and this meeting is supposed to be ending by 10:30. So I believe that will be all for today's class. Thank you all for attending, and I would like to say have a good night's rest. Good night, everybody.